This is going to cover all of our notes for cubics and their graphs. This is lesson 8 of unit 3. We are not going to cover all of the things on this page. We only had enough time during class to get through to about here. Obviously, I will fill these bottom ones in. You can just check them. But we only filled through 3, and then we're probably going to do the other ones as our warm-up. So that's the plan. Up at the top here, it says a blank is a polynomial function that has a degree of 3. That'd be called a cubic function. Remember, degree of 3 just means x cubed. And it says a graphed cubic function is a sideways S, kind of a squiggle shape, that has 1 or 2 blank. That would be called turning points. And those turning points are these right here. So those are also called maxes or mins, as well as changes in direction. And if you look down here at our A through J, you'll notice most of these words look very, very, very familiar because we covered almost every single characteristic during quadratics, which was obviously right before this. There's a few differences. Instead of vertex, we have a center. Excuse me, instead of just a chunk of concavity, like concave up or concave down, now we have intervals of concavity because of our extra degree and our extra turning point. We now can have sections of concave up and concave down, and then everything else is exactly the same. So this top part should go by pretty quickly. The center is just the middle point of our graph. And for the question here, it looks like it's right there. It's going to be right directly in between your 2 min and maxes, or it'll be right there. If you have like a flat area like this, it'll be on that point right there. There is a mathematical term for this. It is called the point of inflection, but you'll learn that later on in breakout. I'm just going to label it here on our graph, and it's at, looks like 1, 2. Put that over here, 1, 2. Go next. B says roots, solutions, x-intercepts, or zeros. Obviously, that's where we touch or cross the x-axis. We have one here and one here. That one is at -1, and the second one here is at 2. And we crossed straight through at that -1, so it would have a multiplicity of 1 right there. Remember, our multiplicity just tells us graphically what it looks like when it interacts with the x-axis. If it goes straight through, it's a multiplicity of 1. If it bounces off like this, it's a multiplicity of 2. And if it squiggles, so like this, but on the axis, so like that, it would have a multiplicity of 3. So then our second one over here at +2, that one bounces off, so it would have a multiplicity of 2. And then if you need just to mark this as x-axis, if that would help you, you can. You don't have to. C says the y-intercept. Again, just crossing the y-axis instead of the x-axis. That's right there. Looks like it's at 4. 0, 4. Next, D says intervals of concavity. I'm just going to have you write down what it looks like to be concave up or concave down. So concave up looks like this. Concave down looks like that. And intervals of concavity run along the x-axis. So are written along x-axis. If I look at the graph here, you'll notice the center right here is where it switches concavity. I'm going to highlight one color for each. So if I'm doing concave down, see, this is concave down because it's facing down. I like to say down like a frown. And if you're ever not sure, you can just continue the graph along in the shape and you'll see a little easier sometimes if it's concave up or down. And then it swaps there at the center and it turns into concave up. This one I like to say concave up like a cup. And you just make a little cup right there. So if I was writing this down, the point that it switches at is the center. I'm going to put it, let's see, put it up here, D. And we are concave up, starting at the center here and forever. So it would start at 1 and then go on to positive infinity. And then for concave down, that one, we are concave down from the beginning up until the center at 1. So that one would be negative infinity until 1. Just like with our domain in any interval really that we're writing, you're always going to write the smaller number first, comma, the larger number. Okay, E is extrema. Remember, extrema are our turning points. They're also called changes in direction. I'm going to write that here. Turning points / changes in direction. And those points are maxes or mins. Max looks like this. And a min is the exact opposite, looks like that. And we're just going to mark those over here on the graph. We have 2 of them. Put E here. Sorry, I forgot to circle those B's. And then another E right there. So for this one here, we are decreasing. Then we hit this point, we start increasing again. So this is a minimum. We'll label that min at. And normally you just put the Y value because that's how low it is on the graph. This would have a Y value of 0. And then for the maximum, same thing, we're going to use a Y value. So max at Y equals, and then it looks like our high point here, this one is at 4 on the Y-axis. Next, F is increasing and decreasing intervals. Like I said before, just like D, intervals of concavity, all our intervals are going to be written along the x-axis. And for these, remember, increasing just means going up, like the Y values are getting larger. And decreasing just means going down, so the Y values are getting smaller. I'm going to write these down here. That was F. So if you look at our graph here, it changes at the turning points. That's why they're called turning points. I'm increasing here until this turning point here, this max. And then I'm decreasing until this min here, and then I'm increasing again. So we have 2 sections or intervals of increasing and 1 interval of decreasing. So I'm going to do increasing first because there's more of it. We're increasing all the way here until we hit this maximum, which is at 0 compared to the x-axis. So from negative infinity until 0. Then I'm going to do this little U that stands for union. That just means and. So I'm saying I'm increasing from negative infinity to 0 and starting again there at 2 until infinity. So we're increasing here as well from here up. And then our interval of decreasing is just this chunk here. We are decreasing from here to here, which is from 0 to 2. Next, we have G and H, domain and range. Domain and range is actually really, really simple for functions that have a odd degree. Remember our degree up here, our degree is 3. When functions have an odd degree, their end behavior is always going to be pointing in opposite directions. And because of that, their domain and their range is always going to be forever. It's going to go from negative to positive infinity, from the left to the right, and from the bottom to the top. So for these ones, if odd degree, always all real numbers. So negative to positive infinity. Next, we have our end behavior. End behavior here, like I just mentioned, if we have an odd degree, the ends are always going to be pointing in opposite directions. I'm going to put odd equals opposite ends, which is different than we just saw with our quadratic functions, which are even functions, right? They're x squared, 2 is an even number. Those ends are always going to be going in the same direction. So for here, what we're going to do is just write out our x value. On the left, x is always going to be going in the negative direction, and we got to figure out y. And then on the right, x is always going to go in the positive direction, and we got to figure out the y. And then for these y's, they're always going to be either positive or negative infinity. One will be positive and one will be negative because they're pointing in opposite directions. Let's put that, stick it up here in this corner. So on the left, remember we always know that x is going in the negative direction. On the right, x is going in the positive direction. Oop, whoopsie. Forgot to draw that y there. There we go. Then if we look at the left, so this is the left side, it's pointing down, so it's going in the negative direction. And that means because it's an odd function, x cubed, that means the right side's going in the opposite direction, so it's going in the positive direction. And what we know by this, we mentioned it before, is a is decided here by this right end behavior. Because the right is positive, that means we have a positive a value, a being our leading coefficient, which is the number in the very front of our equation. There we go. And then last but not least, we have our symmetry. For degree, remember we are an odd degree because it's x cubed. And again, what we know about that is that our ends are going in opposite directions. And then functional symmetry, if we go through 0, 0, so if we cross through the origin, it's going to be odd. If not, then it's neither. So this one does have the potential of being an odd function as well as an odd degree, just like our quadratic had the potential to be an even function, just like an even degree, but it has to go through 0, 0. And there we go. So looking at ours here, this one, obviously symmetry is odd, but its function symmetry is neither because it doesn't cross through the origin right there. Good. Let's go through number 1 and then you can try number 2. So here's number 1. Looking at our graph here, you'll notice this one does not have our turning points like the last one did. It just has one squiggle right there in the middle. This will mean a couple things are different and, in my opinion, at least easier than the one we just went over together. Zeros are first, so we're going to see where we cross through the x-axis. It looks like right here, it's about halfway between. So we'll say negative 1.5, comma 0. It crosses through in a straight line, so it is a multiplicity of 1. The center, remember the center is either right in between your two min and maxes, or if there aren't min and maxes, it's at the middle of that flat part right here, and that is at 0, 3. That does obviously happen to be our y-intercept as well. That doesn't always happen, it just happens to sometimes. Now, mins and maxes, remember those are turning points, meaning we have to go from down to up or up to down. If you look at our graph, it goes up and then it just keeps going up. So it goes up forever. That means there are not any mins and maxes. So we'll just put none here. Our domain and range we already talked about. Because the arrows are going in opposite directions here and here. This one is going to the left and down. This one is going to the right and up. That means we cover from negative to positive infinity on the x-axis and from negative to positive infinity on the y-axis. So our domain and our range is going to be all real numbers, which is just from negative to positive infinity. And behavior here, I'm just going to go ahead and pre-fill out my x's. On the left, I'm going in the negative direction, and on the right, I'm going in the positive direction. And then we'll actually look at the ends. If you look at the left end, this one is pointing down, so that'd be negative. And then because it's an odd function, the other end's going in the opposite direction, so it would be positive. And you can also see that corroborated here on the graph. Because our right end is positive, that means we have a positive a value. Remember, that's called a leading coefficient. We will normally call it LC, which just means that the number in the front of your equation is a positive number. Next, we have concave up and down. Remember, that swaps at the center. So our middle is right here. That means from here to here, we are a different concavity than here up. These ones, in my opinion, are a bit harder to see concavity. So if you just try to follow it, remember, to see what kind of concavity you have, just kind of follow where your pen wants to go. Here you can see we are concave down, because if I kept going, it would go back down. And then here, I'm concave up, because if I were to try to go the other direction, I would go back up again. So I started concave down until our center here at 0. So I'm concave down from negative infinity to 0. And then we start going concave up at the center, which is at 0, until infinity. Increasing and decreasing is easier with these that don't have the min and max, because you're always going to be doing one or the other. If you look at this one, because there is no direction change, right? There's no min or max to change directions. I'm going up, and I keep on going up. So this guy is increasing forever. So increasing would be from negative to positive infinity, and it's never decreasing. You can put never, or you can just put none as if there are no intervals. Either one's fine. Symmetry, remember, degree-wise, we are odd because we're x cubed, which means we know that the ends are going to go in opposite directions, one positive and one negative. And then functional, if we go through 0, 0, it's odd. Because we don't go through 0, 0, it would be neither. Here, so you can see the whole thing. Now I'm going to go through the next one, so just go ahead and pause, see if you can fill in the next one on your own, and then come back when you're ready. Go ahead and check your answers here. I'm just going to pause here for a sec before I scroll back up to the graph. A couple of things I want to point out that are different than the last one that we just tried was the center and the y-intercept are not the same thing this time. You can see that is not always exactly the same. We do have a different order of end behavior this time. So this time the left is pointing up and the right is pointing down, which gives us a negative a value, meaning our leading coefficient, which is the number in the front of our equation, is going to be negative. Our concavity situation obviously still the same. You're always going to switch at the center, the x value of the center. And then this time, instead of having an increasing forever, we actually have it decreasing forever. Here is the graph there. I marked most of the relevant points. And then just to kind of go over a couple of things I think might be confusing, our center right there is where we change concavity. So this is concave up. You can see if you kept going, it would go that way. And this one here, you can see is concave down. If you kept going, it would go back down. And we switch concavity right here at -1. You can see that there. And then our ends, right, this left end is pointing up, and the right end is pointing down, which tells us that we have a negative a value. And there we go. Cool. Go ahead and look at the next page. And we're going to do practice number 3 as well. So go ahead and pause, and then I'll cover it in just a second. Go ahead and check your answer for practice number 3. I did mark a few things on this graph because I feel like it might be a little bit harder. Again, increasing and decreasing, I think, is the hardest one. We also had to round these, and I forgot to mark them for you beforehand. So if you want to mark them and then don't look at the box and pause again, you can. I estimated this to be at 0.8 comma negative 10.5, because I feel like that makes close enough to the most sense. And then this one, because it is obviously symmetrical, would be at negative 2.8 comma positive 10.5. And then you'll be able to see that I use those values here in my box. So our x-intercept, we do cross the x-axis 3 times here, here, and here, all with a multiplicity of 1 because they cross straight through in a straight line. We have -4, -1, and 2. Our center is right here at -1, 0. And then our y-intercept is here at 0, 8. We do have a min and max, one of each. For these graphs, you might have already noticed you either have neither or both. And the type of min and maxes we do have on odd functions, or odd degreed functions, apologies, is going to be called a relative minimum or maximum. It just means that your hump is part of a graph that has ends pointing further up and further down than your min and your max. So the other option would be absolute min and maxes. We see those in quadratic functions. So when you have a quadratic function that looks like this would be called an absolute maximum. And that's because there's no other point on the graph that is higher than that point. But on ours, for odd functions, and this is true for all odd degreed functions, so x cubed, x to the fifth, etc., it will only have relative ones because it's never going to be the highest point ever, because the graph's always going to be pointing farther up or farther down if you're looking at a minimum on either end because of the nature of the end behavior. So I wrote down both my mins and maxes. I just put down the y equals part. If you want to write the whole point, you can. That's also correct. Here for our domain and range, as we've already spoken about, if you have an odd degreed function, you're always going to have all real numbers here. I just wrote it out this time. And then I wrote the symbol for all real numbers on this one, just in case. I'm not sure if you will see that later on, but you might. So just in case, this symbol also means all real numbers. Our end behavior here, we are going down on the left and up on the right. Remember, if the right is positive, that means our leading coefficient, our a value, is also positive. We are concave up for this section here from the center forever. And then we're concave down starting over here until the center. Remember, that's against the x-axis, so I picked that -1 because that's where it is on the x-axis. And then our increasing or decreasing, I did mark those on the graph. I thought that might help. Remember, increasing just means the y values are getting larger from left to right, and decreasing means the y values are getting smaller from left to right. We read it left to right because that's how we read in English. So here, we're increasing from -infinity until this max point, which we decided was -2.8. And then we're increasing again from this minimum point at 0.8 until forever. That's right here. And then the in-between section is the only part that's decreasing, and that is between the min and the max right there. And then our symmetry, it's an odd degreed function because it's x cubed, and the function does not have either a rotational or a fluxional symmetry because it doesn't go through the origin at 0, 0. Hopefully this was helpful. The absolute and relative min and max thing, we will cover more later on. I just want to make sure that you saw it somewhere. If you want to fill it in, we can write it right here. Absolute min / max means the low or high point on a graph only in even degree functions. I think my dog's about to bark. I just want to warn you. I'm sorry if she does. And then relative min and max are all of the other ones. They do also include absolutes. It's any min and max ever. And those are the kind that we have here on our function. Okay, perfect. Hope this helped. Bye.